Hi everyone, my name is Max Morrison, and today I'll be telling you about our paper, Controllable Neural Prosody Synthesis. This is work I performed while an internship with the Adobe Audio Research Team, working with Seiyu Jin, Justin Solomon, Nicholas J. Bryant, and Gautam J. Mysore. Speech content creators, such as voice actors and podcasters, often re-record the same content many times, fine-tuning details such as the wording, the placement of emphases, and the prosody. It would be nice if we could just record once and quickly edit in an intuitive manner to create a similarly high-quality result. As well, existing text-to-speech systems aren't able to change the prosody after the fact. This is a problem because the prosody can change the meaning of a sentence. For example, in the sentence, I am going to the store, if I say, I am going to the store, that disambiguates who's going to the store. And if I say, I am going to the store, that tells where I'm going. Our work proposes solutions to both of these problems by allowing users to intuitively edit the pitch component of the prosody. Let's see an example. Here we see text as well as a corresponding pitch contour at which that text is spoken. Let's listen.
He passed from the trembling bridge on to firm land again.
Now let's say we wanted to add an emphasis over the word trembling. This would be very difficult to do in an existing digital audio workstation. However, it's very easy to do with our system. Here, a user simply draws the pitch that they want over trembling. Here we have a higher pitch corresponding to an emphasis. And then our model takes as input the user's constraints as well as the input text features and generates a new prosody contour for the text. Let's listen to the result.
He passed from the trembling bridge on to firm land again.
The rest of our talk will be structured as follows. First, we'll describe our methods both for generating the pitch component of prosody as well as applying the generated pitch contours to the speech waveform. After that, we'll talk about evaluating both our prosody generator and our pitch shifting vocoder. Note that all of the red text corresponds to contributions made in our paper. As a baseline model for prosody generation, we use the deep autoregressive or DAR model proposed by Xin Wang et al. In 2017. This model takes as input features derived from the text and produces a pitch contour at which the text can be spoken. The architecture consists of two fully connected layers, followed by a bidirectional RNN, and then a unidirectional RNN. The unidirectional RNN is autoregressive. This means at time frame t, the network will predict distribution parameters, in this case parameters of a categorical distribution, and then before the next frame, we'll take a sample from that distribution. Early in training, the samples generated tend to be pretty bad. Instead, we use teacher forcing, where instead of passing these bad samples, we pass the ground truth observations. Now this induces another issue where the network never sees the errors made in its history and never learns how to deal with them. Techniques such as data dropout and scheduled sampling alleviate this issue called exposure bias. In the original DAR paper, they proposed data dropout. For our paper, we use scheduled sampling, and we found that the two are rather comparable in terms of subjective naturalness. In addition to the scheduled sampling, we add two additions to the DAR model. The first is the postnet architecture. This is inspired by the postnet from Tacotron 2, and it consists of 5 convolutional layers, each followed by a nonlinear activation. Now, we'll get more into this postnet later, but for now, let's notice 2 interesting things. One, there are now 2 places where the network predicts distribution parameters. And 2, while the autoregressive receptive field is causal, meaning the receptive field at time t is everything up to frame t, the receptive field after adding a postnet is non-causal, meaning that the network can lurk a couple of observations into the future. In addition, in order to make our network context-aware, meaning the prosody generated may sound good relative to previous and following speech, we take features from the previous and following speech and summarize them using untied bidirectional GRUs. Now that we've seen how we can generate the pitch component of prosody, let's see how we can take the generated pitch and apply it to a speech waveform. Prior DSP-based methods for pitch shifting speech include World, as well as time domain Pisola, the manipulation algorithm used in the Pratt software. More recent neural methods include quasi-periodic WaveNet, which considers the pitch shift as a change in the dilation rate of a WaveNet. However, the subjective quality of the resulting samples are rather low and comparable to the World vocoder. As well, many latent variable solutions exist in which the authors show that traversal along some direction in a latent space corresponds to a change in pitch. However, it's unclear how to achieve control over the pitch over the entire speaker's range using these methods. As well, some very recent methods include fast speech and fast speech 2, both based on the fast speech architecture, and both of these show very good pitch-shifting neural vocoding performance. Our proposed method for a pitch-shifting neural vocoder is a modification of the WaveNet vocoding architecture. We take the input speech and compute the 21-dimensional MEL-substral coefficients. These spectral features are passed into a neural bottleneck consisting of 3 convolutional layers of 20, 20, and 12 channels, respectively, with ReLUs in between. As well, after the bottleneck, we provide an explicitly given target pitch contour. The intuition here is that the bottleneck needs to squeeze out all the pitch information of the MEL-substral coefficients, and ideally the network learns to take pitch information only from the explicitly given target pitch contour. Let's recap our proposed method. From input text and corresponding speech, we first pass the input text through a prosody generator, which produces a pitch contour at which the text can be said. The user may provide constraints, in which case it's the job of the prosody generator to fill in the blanks. The generated pitch is used as conditioning to a pitch-shifting vocoder, which produces speech that follows the given pitch. The prosody generator on the left is our proposed C-DAR model, and the pitch-shifting vocoder on the right is our proposed pitch-shifting WaveNet. Now that we've discussed our methods for both generating the pitch contour of prosody and applying it to a speech waveform, let's talk about how we can evaluate our models. In order to evaluate our prosody generator, we first have to deal with an issue, and that is that pitch shifters often create larger artifacts when the pitch shift is large. This is a problem because that means that any prosody that's generated with a high L2 distance from the original prosody is going to sound less natural, whereas it might actually be a very natural way to say the underlying text. Our solution is to low pass at 10 Hz above the fundamental frequency to remove all these additional artifacts and only preserve the fundamental frequency contour. Let's hear some examples. For each of the 3 examples here, determine whether you think that the sample was taken from real speech or generated from synthetic speech. Here's number 1.
The red had turned to mauve, the mauve was becoming violet, and then clear blue.
Number 2.
The red had turned to mauve, the mauve was becoming violet, and then clear blue.
Number 3.
The red had turned to mauve, the mauve was becoming violet, and then clear blue.
And we find that the first example is real, the second was synthetic, and the third was generated by our proposed C-DAR model. We provide our samples to Amazon Mechanical Turk workers and ask them whether they believe that the sample is real or synthetic. For a high-quality anchor, we use the original prosody, which is considered real 72% of the time. For low-quality anchors, we use monotone, which is considered real 19% of the time, as well as 2 random baselines. For random swap, we swap the pitch contour of words within the same sentence, and for random replace, we swap the pitch contour of each word with some word in any other sentence spoken by the same speaker. As well, we include our two neural models, DAR and C-DAR. We find that the performance of DAR and C-DAR are somewhere in between our high and low quality baselines. This means that there is still room for some significant improvement in prosody naturalness. As well, we experiment with some objective metrics for prosody generation, including negative log likelihood and the root mean square error. We find that neither of these correlates well with subjective preference of English prosody, most likely due to the assumption that these metrics make, that prosody is unimodal. However, for English prosody, we find that this is not a good assumption. Next, we evaluate the extent to which each of the prosody generation models can be controlled. We propose the repunctuation task, in which the goal is to make questions sound like statements and statements sound like questions. Let's hear some example of this. First, we'll turn a statement into a question. Here's the statement that we will change.
His nerves were completely shattered, and he started at the slightest noise.
And here is the question-like prosody generated by our model.
His nerves were completely shattered, and he started at the slightest noise.
Next, let's take a question and turn it into a statement. Here's an original question.
Why hadn't his own fuzzies attracted as much notice in the 3 weeks since they had vanished?
And here is the statement-like prosody generated by C-DAR for this text.
Why hadn't his own fuzzies attracted as much notice in the 3 weeks since they had vanished?
As before, we low-pass filter our speech samples to remove any vocoder artifacts. We then provide pairs of samples to Amazon Mechanical Turk workers and ask them which one best represents the target punctuation. Let's go over the conditions. For the original condition, we do not change the prosody at all. This means that it should not reflect the target punctuation. If we're trying to change a statement to a question, the original should still sound like a statement. For the heuristic, we take the original prosody and change only the last two words. We make sure questions end upwards and statements end downwards. For both DAR and C-DAR, we both change the text so that if it ends with a period, it instead ends with a question mark, or vice versa. As well, with C-DAR, we change the last two words to make sure questions end upwards and statements end downwards. We'll take a couple of observations. One, our model is significantly more capable of generating question-like prosody relative to prior prosody generation models. As well, prior models are quite bad at generating question-like prosody. We think this is because question-like prosody is underrepresented in text-to-speech datasets. In other words, this is a form of mode collapse. Now let's discuss the qualitative effects of using a postnet in our architecture. If you remember, the addition of the postnet caused two things. One, there are now two places in our network where we're predicting distribution parameters. These are before the postnet on the top and after the postnet on the bottom. And two, the postnet has a non-causal receptive field. So in this top graph, the causal receptive field causes a frame of high variance, which leads to a sampling error. But because we have a non-causal receptive field in the postnet, we're able to fix that sampling error. Lastly, we evaluate our pitch-shifting WaveNet vocoder via both objective and subjective evaluation. For objective evaluation, we perform pitch shifting with a target pitch contour. We then take the output speech and perform pitch tracking. We want the input target pitch to match the output pitch. We want it to match in multiple ways. We want it to match both in the voiced regions, having low RMSE, as well as in the unvoiced regions. And we measure this with the precision, recall, and F1 score of the voiced-unvoiced decision. Lastly, we perform subjective evaluation. Here, we give samples to Amazon Mechanical Turk workers of both pitch-shifted and non-pitch-shifted speech and ask them to provide mean opinion scores. Let's hear some examples. You'll hear two examples where we'll play original, and then we'll play world, Pisola, and the proposed pitch-shifting WaveNet vocoded speech with the same pitch contour. Here's the first original example.
Please don't be angry with me. If you'd let us be engaged last year, there would never have been all this trouble.
Next, we're going to take a new target pitch contour and vocode the same speech using world.
Please don't be angry with me. If you'd let us be engaged last year, there would never have been all this trouble.
Now that same pitch contour with Pisola.
Please don't be angry with me. If you'd let us be engaged last year, there would never have been all this trouble.
And lastly, our WaveNet vocoder.
Please don't be angry with me. If you'd let us be engaged last year, there would never have been all this trouble.
Now for our second example, this will come from a new speaker.
Can you discover by your magic whether or not it is a witch?
Next, with a new pitch contour using the world vocoder.
Can you discover by your magic whether or not it is a witch?
Next, using the same pitch contour, but the Pisola vocoder.
Can you discover by your magic whether or not it is a witch?
And lastly, our proposed pitch shift WaveNet.
Can you discover by your magic whether or not it is a witch?
For a high-quality anchor, we use the original speech signal, which achieves an MOS score of 4.3. For our low-quality anchor, we use the 3-bit quantized signal, which achieves an MOS of 1.5. Next, we take the original pitch contour and pass it in as the target pitch to Pisola, world, and pitch-shifting WaveNet. We find that relative to an unbottlenecked WaveNet, our MOS score is slightly lower. This indicates that our bottleneck is squeezing out a little more than just the pitch information. Next, we use C-DAR and DAR to generate new pitch contours and use Pisola, world, and pitch shift WaveNet in order to perform pitch shifting. We find that our model outperforms the world vocoder and performs roughly comparably with Pisola. In conclusion, we present our paper, Controllable Neural Prosody Synthesis, in which we contribute a controllable, context-aware speech prosody generator, a pitch-shifting WaveNet vocoder, and novel methods for the subjective evaluation of prosody. If you'd like to hear more examples, you can find them at maxrmorrison.com/sites/controllable-prosody. Thank you for listening.